Good morning, everybody. We're going to continue looking at the gradient. We're going to continue looking at the slope of graphs today, except we're going to look at them under the scope of what's called the derivative function. So we're going to be using this word derivative a lot. And so basically what I need you all to understand, this word derivative, this just means the function that's going to tell us the gradient or the slope function. And so basically, for a non-linear function, a function that's not a straight line, the gradient or the slope is going to change as we move along this curve. So like if we had a curve, like a parabola, the slope here is not the same as the slope here, is not the same as the slope here, or here, or here. It varies. And so what we can actually do is we can write a gradient, a slope function, for any function y equals f of x there, and we call that function that tells us the slope at any point, we call that the derivative function. And so we represent the derivative function in a couple different ways. One of the ways that you're going to see it is f prime of x. So anytime that you see this notation right here, f prime of x, we are referring to the slope of a function, not necessarily the original function itself. Now, on a problem set last class, it was number 2 from last class, we looked and saw that the function was y equals x squared, and you should have gotten that the pattern with the gradient, the pattern with the slope for y equals x squared is that the slope was always double the x coordinate. So like the way that we would represent this, we have our original function right here, f of x equals x squared. And then we have the gradient function right here, which just says you're going to take 2 times x. And this is our gradient, this is our derivative, this is our slope function. And so they work the same way. If we want to get any coordinate, we just substitute an x value into here and we get the y value. If we want to get the slope of any coordinate, we substitute into the derivative slash the slope slash the gradient function. So I want to look at a couple of examples of this with you all. So I'm actually going to pull up this graph in your book. So this is going to be example 6 on page 294, mainly just because I don't trust myself to draw a perfect graph here. So if we look at this, example here, we've got this graph, and what we want to find is we want to find f prime of 4. Now, all that this is saying is that we want to figure out what the slope, the instantaneous slope at the coordinate of 4 on f of x is. If we wanted to find actual f of 4, we'd need the coordinate. But what we've got this tangent line right here. And so with that, 2 coordinates that this tangent line passes through, it passes through the coordinate 2, 0 right there, and it passes through the coordinate 6, 4. And so really we just want to know, okay, what is the slope between these 2 coordinates? So again, if we say that's x1, y1, and x2, y2, let's see, y2 minus y1 over x2 minus x1, or the rise over the run. We get 4 minus 0, 4 minus 0 over 6 minus 2. So that's going to be 4 over 4. Oh, I'm going off the screen here. That's going to be 4 over 4, or 1. So if you take the gradient of this tangent line at the x value of 4, the slope, the derivative function there is going to give you 4. And so you look there, and they've got that work posted right there. So with that, so all the derivative function does is it tells us what the slope is. It tells us what is the slope at a certain x value. And so there's a couple of different ways that you can see this. If we are given y equals f of x for some function, we often will write it, the derivative, as you'll see it as dy over dx. This is called the derivative of y with respect to x. If you actually see that That's how you say that. Another way that you'll see it is dy by dx, so derivative of y by the derivative of x. And just to solidify that notation, we have y equals x squared, then dy over dx equals 2x. The derivative of y with respect to x is just 2x. So that's just a little bit of notation for you. So looking at this now, so we're going to go over to number 4 on page 255. And so for this graph right here, so we're going to be looking at this particular problem. So we've got this graph right here. This is y equals f of x. It's some sort of parabola. The derivative function, the function that gives us the slope of this at any given point, is f of 2x, or f prime of x equals 2x plus 1. And so what we want to do is we want to find and interpret f of negative 2, or f prime of negative 2, excuse me, and we want to find and interpret f prime of 0. So let's go ahead and solve for that. So if you've got your derivative function right here, you're going to evaluate this the same way that you would just a regular function. So if we do f prime of negative 2, f prime of negative 2, we're just going to substitute in for x there is 2 times negative 2 plus 1. F prime of negative 2 is going to be negative 4 plus 1. F prime of negative 2 is negative 3. Now, what this means here is that the slope at x equals negative 2 is negative, and also what that means is that the graph is decreasing. If the slope is negative, the graph is decreasing. And if we pull up this graph again real quick, you can see if we go to the x value of negative 2 right here, that this graph is decreasing at this point in time. If you read it from left to right, it is going downward. So then we're going to do the same thing for 0 here. So if we go to 0, you can see right there at that point, we haven't calculated it yet, but as we should go in, it should be positive slope because it goes to increasing at that point. So let's go ahead and calculate that just to kind of confirm, and then we will look at some other types of examples. So if we're doing f prime of 0, let's see, f prime of 0, that's going to be 2 times 0 plus 1. So the slope at the x value of 0 is just going to be 0. So again, the way that you interpret this, that the slope at x equals 0 is positive, which again means that the graph is increasing. The graph is indeed increasing. So that is kind of it for that section. So then the second section that we're going to look at today is called differentiation. Now, this word differentiation here, this is just a fancy word to say finding a derivative. This is the actual mathematical act of you finding a derivative. And so we looked earlier that the way that you can find the instantaneous slope at a point is to use this definition, the limit definition right here. And it turns out that you can actually use that definition to find the derivative of any function. And so to find the derivative for any function, y equals f of x, we're going to calculate the instantaneous slope just by doing this limit definition. So if you're trying to find f prime of x or dy over dx, this is actually, you're just going to do the limit definition that we've already kind of looked at together as a class. And so whenever we do this process here, whenever we evaluate this limit to find a derivative, this is called differentiating from first principles. And this is the longer way to do a derivative. So if you hear this word, do first principles, you're like, all right, well, that means I have to do this the longer way. So let's look at an example here. And so I'm going to write down this limit definition here real quick. The limit as h approaches 0. I would recommend writing this down as well. It's very easy to forget. So let's look at this limit definition together. So we want to find, we know from earlier that the derivative of x squared should be 2 times x. But let's use this limit definition to show that. So if we substitute in x plus h, so again, we've got x, we've got y. If we substitute in x plus h into x squared, we're going to get x plus h squared. And actually what I'm going to do is I'm going to go ahead and expand this so that way I don't have to do all that work later. So if I do x plus h times x plus h, that's just what this is equal to. We get x times x, which is x squared, plus xh, plus xh, plus h squared, so that's x squared, plus 2xh, plus h squared. Now, this is what we get if we evaluate x plus h. Now, we don't have an actual point to plug in here, so when we subtract f of x here, so this is f of x plus h right here. F of x is actually just x squared here. So when we write this limit definition out, we're going to say the limit of h as h approaches 0 of f of x plus h, that's this part right here, x squared plus 2xh plus h squared, and we're going to subtract f of x here, which is minus x squared, and we're going to divide this by the horizontal distance. Again, this formula right here, this limit is really, we're just doing the slope, and then we're going to take the horizontal distance and push that to 0. So if we simplify this right here, you can see these x squareds right here are going to cancel out. So then what we've got 2xh plus h squared divided by h, and we're taking the limit as h approaches 0. So then here, both of these things have an h, so what I'm going to do is I'm going to factor out an h from both of these things. I'm going to factor out an h from both of these things. So we got h parentheses 2x plus h divided by h. We can cancel those things. So now what we're really doing, I need to write this over here. I'm out of room. I apologize. So the limit as h approaches 0 of 2x plus h, if we substitute 0 in for h, we're just going to get the 2x. It's going to be 2x plus 0, which is just 2x. So this right here, so f prime of x is actually just 2x, which we've kind of looked at a few different ways the past couple classes. The derivative of x squared is 2 times x. And so what we're going to do is we're going to look at a couple more of these first principle ones, just actually calculating these derivatives by hand today, and then we are going to call it a day for today. So the next one that we're going to look at, we've got f of x equals 2x minus 1. So let's see here. I'm going to write out the limit definition. The limit as h approaches 0 of f of x plus h minus the f of x over h. Again, that's just our slope definition. So let's see. I need to figure out what x plus h is. So if I substitute this in to 2 times x minus 1, that's going to be 2 times x plus h minus 1. So if I distribute here, that's going to be 2x plus 2h minus 1. So this is what f of a plus h is. So what we're going to do is we're going to substitute this in. So we're still taking the limit as the horizontal distance goes to 0. And we've got a plus h, so that is 2x plus 2h minus 1 minus f of x here. Now f of x, we're going to subtract the quantity of 2x minus 1. And then we're going to divide by h. So let's clean this up a little bit. Let's do just a little bit of algebra. As h approaches 0, we have 2x plus 2h minus 1 minus 2x plus 1 divided by h. So this 2x is going to cancel with this minus 2x. This minus 1 is going to cancel with this plus 1. And what we're left with is the limit as h approaches 0 of 2h over h, which is the limit as h approaches 0 of 2. Now, I had a couple conversations with you all about the what happens if we make h 0 when the limit, we're taking the limit and the function is 2. No matter what you plug in for h, 2 is always going to be 2. It doesn't matter if you do 0, 1, 2, 3, 4, 4.5, 17. It's always going to be 2. So the derivative function is just the f prime of x is going to be 2. And as a reminder, just the regular old f of x here was 2x minus 1. So this function is, so it's going to be a constant slope of 2, which makes sense because the parent function is 2x minus 1. This is, if you graph this, this is a straight line with a slope of 2. So as you're working these, ask yourselves if that slope that you're calculating makes sense. You can look at that graph and see if it changes or if it stays constant. And typically, any linear function is going to have a constant slope because it's a line. It goes up at a constant rate. So then the last thing that we're going to look at today is we're going to do the derivative of a cubic function. So the first thing I'm going to do is I'm going to show you all how to use a calculator to calculate a derivative real quick. And then from there, what we'll do is we will actually calculate it by hand, and then we'll call it a day for today. So with that, the first thing that we're going to do, we've got the function y equals x cubed here. Y equals x cubed. So the first thing we're going to do is use a graphing calculator to find the gradient of the tangent for the following x values. So we're going to calculate the derivative here. So if you go to your TI-84 graphing calc or whatever you're using as a graphing calculator, what you can do is, so if you go to y equals, and we look at that, if you go to math and you scroll down, the 8th option here where it says the derivative, in derivative, what you're going to do is you're going to say dx, and you're going to say, okay, well, let's look at the derivative of x to the third for all x is equal to x. That's just going to say for all x values. We want to look at this derivative. So we go and we graph this thing. Can you... So let's see. If I go to second and I go to table, okay, that's going to get me where I want to go. It doesn't calculate as easily as it does on the actual calculator. So we're going to go from a table start of 0. We want the change in the table to be 1. And then what that's going to do is if you go, oh, what just happened? If you go to table here, no, I need to go to second, table set, do 1, okay. And then table, so there we go. We're doing just fine now. So for -3, the derivative there is going to be 9. For -2, the derivative is going to be 4. It's positive slope, it's increasing. For -1, the derivative here is going to be 1. And let's see, we got 0, 0, 1, 1, 2, 4, 3, 9. So that is the alleged derivative according to technology. So now we are going to, so to help us calculate the derivative on C, we're going to prove that x plus h to the third power equals this expanded polynomial right here. So to do that, I'm just going to write out 3x plus h's, and we're going to do a little bit of math to show that. So if I distribute between these two first terms, x times x, I'm going to get x squared plus xh plus xh plus h squared, and this is times x plus h still. So then if I combine these two, I'm going to get x squared plus 2xh plus h squared, and this is being multiplied times x plus h. So now we've got to distribute one more time. We got to double distribute. X times x here is going to be equal to x cubed. Okay, that's where that's going to come from. X squared times h is going to be x squared h. 2xh times x is going to be 2x squared h. 2x squared h times h. It's going to be 2xh squared. We've got h squared times x. That's going to be h squared x. And then h squared times h is going to be h to the third power. So we're looking, is there any common terms we can combine? We can add this one and this one. We can add this one and this one. So we get x cubed plus 3x squared h plus 3x h squared plus h cubed. So we have just shown that x plus h to the third power is equal to this. Now this is important because we're going to use this here in just a second. We're going to use this to calculate its derivative. So now we're going to do the derivative of f of x equals x cubed from its first principle. So we're going to use that limit definition of f of x plus h minus f of x divided by h. Now, lucky for us, we just calculated what x plus h cubed is going to be. If we plug in x plus h cubed into there, we're going to get this long expanded thing. So I'm going to replace that. I'm going to start down here because I need a lot of room. This is kind of long and tedious and drawn out. That is okay. It be like that sometimes. Plus h cubed. So that's this whole expression right here. We got minus, so f of x here is x cubed. So we're going to say minus x cubed, and then we're going to divide this whole thing by h. So let's see. We can cancel out this x cubed and this x cubed. Those are going to go away. And now there's an h in everything. So what I'm going to do is I'm going to factor out an h. So then that'll be 3x squared plus 3xh plus h squared divided by h. And I can cancel out, I can divide out one of those h's. And so then the last thing that we can do here, we've got the limit as h approaches 0 of 3x squared plus 3x times h plus h squared, is we're just going to set h equal to 0. There's no restrictions on it. So if I do 3x squared plus 3x times 0 plus 0 squared, these disappear, and what we're left with is our gradient function. It's our derivative. We have just differentiated this thing. So our f prime of x, again, to try to use all this nice vocabulary that tells us our slope at any point, is 3x squared. And so again, if you wanted to confirm this, what we could do is if we go back to our, so we said f prime of x was 3x squared. If you substitute in any of these x values right here, if you substitute in any of those x values, we should get back to our, we should get to these values right there. We should get to those values right there. And so with that, So if you have any questions at all, please let me know, and we can definitely look at this together. Other than that, I hope that you all have a good weekend, and I will see you all on Tuesday.